Hello everybody. We discussed today CMOS logic. In the last class we discussed TTL, transistor logic based circuits, okay, and we will cover CMOS logic of course and its various configurations like tri-state and open drain, and when it is used together with TTL in a circuit, how to interface. But we shall begin with a brief discussion on NMOS logic. Okay. So, a MOS device, you know, is a field effect device which offers very high input impedance because it is the input is connected to an insulator oxide layer, but it can be used as a inverter just like what the transistor based BJT based inverter that we had used before, okay, with the exception of that RB is not required. So, this is similar to what we had in earlier case RC, but RB is not required, okay, because it is connected to a insulator, okay. Its input impedance is very high, right, and this is a n channel enhancement mode MOSFET that we are using here, right. N channel is used for electron has got higher mobility. Enhancement, that means when a particular voltage is applied, that is called threshold volt, a layer is N channel is formed, and as long as the voltage remains more than that, the channel is there and the current flows, and if it is less than the threshold voltage, the channel is not formed and the current will not flow, okay. So, Vi need to be greater than the threshold voltage, or this VGS need to be greater than the threshold voltage, and at that time if you increase this is your drain, this is your gate, and this is your source. If we keep increasing the drain to source voltage, right, the current will increase linearly in the beginning, but after that there is a effect called pinch off effect when this VDS is equal to VGS minus VT, okay. At that time because of the pinch off effect, beyond that VDS is going beyond VGS minus VT, the ID, the drain current will remain constant. This drain current remaining constant here is termed as saturation, which is different from the saturation region we had discussed in case of bipolar junction transistor, where an equivalent IC versus VC curve we had seen. So, in the IC versus VC curve that we had seen in case of bipolar junction transistor, this region was the saturation region there, if you remember, okay. When the collector emitter VC voltage was 0.2 volt or 0.1 volt of that sort, both BC junction and CE junction was in forward bias. However, in this particular case, this region is called saturation region. So, this difference is to be noted not to get confused, and this region when the VGS is greater than VT and the current increases with increased value of VDS, that is called linear region or called triode region. And you have got two different equations. This is one equation which is there in the saturation region. So, this saturation region is similar to active region is in our earlier discussion, and this equation we shall use later. Keep take note of this in CMOS discussion, and this is the equation when it occurs for linear region, okay. And what people have done, in the NMOS based logic development, this resistance manufacturing, because now the resistances are very high. So, this high resistance manufacturing it takes lot of space. So, instead of that, a NMOS driver based NMOS transistor based load with gate and source, gate and drain connected in this manner, which offers a approximately linear when this VGS and VDS are constant. So, you can see the current variation with voltage is approximately linear. So, that is used as a instead of a actual resistor as a load which offers less amount of space, requires less amount of space. And for the NOR logic and NAND logic development using NMOS gate, you are having this particular inverter, similar to what we had done in case of RTL circuit or electrical switch based circuit. For NOR, another transistor will come in parallel, and for NAND another transistor will come in series. Okay. So, this is the standard thing that we had followed. The similar thing is done for NMOS based logic gate development also. But one issue that we take note of here is that when this transistor is on, T1 is on, the resistance must be sufficiently small compared to resistance 2, I mean, which is resistance offered by the transistor 2, otherwise the output will not be considered sufficiently low. Okay. So, if it is if both of them are same, then what will happen? The output will be 0.5 of 50% of VSS, which is not sufficiently low. We want to make it as low as possible, right. So, this T1 resistance will be sufficiently small compared to resistance offered by T2, that we take note of. Okay. Because of which, in the NMOS based circuit, we are having an issue that the output where the capacitor plays a very important role at the output junction, charging and discharging of it, because the current the next stage will take is very low, of the order of picoampere or so. So, this charging of the capacitor by this particular resistance, which is relatively high, takes more time, okay, than the discharging of it. Okay. So, which limits the speed, which brings an element of asymmetry. So, from NMOS based logic inverter circuit, we have moved to CMOS based circuit, where the particular part is replaced by a PMOS. Okay. So, how PMOS works? While in NMOS, when we look at the working of the NMOS, so basically you are placing a positive voltage above a threshold voltage, which attracts electrons, and a N channel is formed, okay, and the current conducts. In case of PMOS, what will happen? We want to form a channel made up of holes. So, a negative voltage, relatively negative voltage needs to be applied. Okay. So, if the source and substrate of it is connected to a positive supply, say 10 volt over here, right, and the threshold voltage for this PMOS is 2 volt, then 8 volt or less would be required at this side, at the input side, then only the PMOS channel will be formed, okay, and it will conduct, right. So, when it is at low, which is of course much less than this 8 volt, so channel is formed, so PMOS is on, right, and when it is at low, then of course it is less than 2 volt, so the NMOS will be off. And the other case, when it is 10 volt, right, so when it is 10 volt, so this is 10 volt, this is 10 volt, so it is not sufficiently negative, this particular junction, right. So, no P channel is formed, but it is sufficiently, this particular is sufficiently positive above the threshold voltage, so N channel will be on. So, at any given point of time, you have got either of PMOS or NMOS on, okay, and only during transition or the switching, both of them can become on. Okay. So, because of which, and this PMOS on, the PMOS is made in such a manner that though the mobility of hole is less, that the output resistance is symmetrical for both the cases, about of the order of say 1 kilo ohm, okay, and the charging and discharging is faster compared to what we had seen before. The other important thing here, there is the when it is either 0 or 1, no power consumption is there along this path, okay. Only during switching some power consumption will be there, okay, and also for during switching when this output capacitor is getting charged or discharged, okay, getting discharged. So, during that process some power consumption will be there, but during static condition unlike in this particular case when it was on, right, when it was on, okay, so there was a current flowing, so that situation does not arise here. And input resistance of such a CMOS is very high, 10 to the power of the order of tera ohm, and capacitance is of the order of 5 picofarad. This capacitance that which will come in the form of a shunt. With this we go to CMOS transfer characteristics, and if we look at the CMOS transfer characteristics, this is the Vi versus Vo plot, okay, and it has got 5 distinct zones, okay. So the first zone that we look at is the case when the input voltage is less than the threshold voltage of the NMOS, okay. So when the input voltage is less than the threshold voltage of the NMOS, what is happening at that time? The T1, the NMOS is off, and at that time, of course, this is sufficiently small, right. So if it is 0 volt or 2 volt, so 10 minus 0 volt or 2 volt, it is sufficiently small, and a channel is positive channel is formed, so for which T2 remains on, okay. So this is what you see over here. Next, the other case when the input voltage is more than that 8 volt that we had talked about, okay, more than 8 volt. That means the P channel it does not get properly formed, okay, it is below the threshold voltage. So when Vi is greater than 8 volt, okay, so Vi is greater than 8 volt, what is happening? T1, T2 is off, but at that time definitely the N channel has got a voltage which is more than the threshold voltage, so for which T1 will remain on. So these are the two cases, two extreme cases we have seen, okay. And we have already noted earlier in case of that NMOS logic inverter discussion that the pinch off occurs when VDS is equal to VGS minus VT. We remember that, okay, for the NMOS. So whenever VDS is greater than VGS minus VT, right, that will be the saturation region then. So this particular case, when you map it to this the corresponding voltages, right. So this is happening when the V naught, right, V naught is your VDS and this VGS is your Vi, okay, and 2 volt is your the threshold voltage that we have considered for the NMOS, also for the PMOS. So when this V naught is greater than Vi minus 2, the saturation for T1 occurs, okay. So V naught is equal to Vi minus 2 is this line, and V naught is greater than Vi minus 2 is this zone, okay. So in this zone what we see that T1 is in saturation, T1 is in saturation, and if we look at the corresponding thing for T2, when T2 will remain in saturation, just similar thing but applied to PMOS. So V naught less than Vi plus 2 when it will be remaining in saturation. So this is the other case, not of course up to the threshold voltage up to this point. So this will be the case when the T2 will remain in saturation. So both T1 and T2 remain in saturation in this zone, okay, and the rest of the zones are defined in this manner: T1 in saturation but T2 not in saturation, T2 in saturation but T1 not in saturation, okay. This is the other two. So when T1 and T2 both are in saturation, and if we apply this equation that we have shown in the before, so we get a unique solution for the voltage when both of them are in saturation. And if we use this particular values, so we get that for 5 volt for the transistor parameters of both of them called Kp and Kn being same, which implies that there is an abrupt jump, okay, at this particular voltage 5 volt in the inverter characteristics. In actual practice, it will be a little bit tapered, it will not be a abrupt jump like this. So this is how the CMOS transfer characteristics it works, and from that we can define VIL, VOH, right, VOL IOH, all those things can be defined. For example, VIL in this particular case, definitely we can consider up to say 2 volt or even little bit more than that. Okay. So, similarly the VIH is, you can see that is relatively higher, which is an important thing to be noted. So, VIH is more than say 6 volt in this particular case, that will be for us to say, simply consider. Okay. So, this is the kind of thing which is happening for these particular values that we have considered, right, and accordingly the manufacturers will tell you for different supply voltages. You remember the CMOS works over a very large range of supply voltages from 3 to 18 volt compared to near about 5 volt for TTL based logic gates. So, one particular example for a 5 volt supply cases, the different kind of parameters that you get. So, as we said, the supply voltage is say 5 volt, then corresponding VIH is 3.5 volt, 3.5 volt, that is what is considered. Okay. If it is 10 volt, almost equivalent to that 7 volt, I mean that region. So, 8 volt is the case when the the another region that we are entering into, okay, the 5th region that we entered, okay, and VIL is 1.5 volt that has been considered, VSS is 5 volt, VOH is again almost equal to 5 volt, okay, when this is for VT is equal to 1.5 volt. If I go back, so this is your the corresponding VOH, okay, the 10 volt, it is almost 4.99 volt it has been considered, and corresponding it is 1.5 volt. So, these are the different things if you can compare from the previous diagram for a different kind of VSS and VT, okay. So, which is coming from the manufacturer's specification. And the other important thing to be noted here are the current level. The current levels are very small, okay. So, the input current is 10 picoampere and minus 10 picoampere. So, basically the two cases when it is high or low, and the corresponding meaning we all understand that it is going into is positive and going away is negative, okay. And similarly the IOH and IOL, the amount of current it can deliver or it can sink. So, these are the two important parameters for us to take note of, okay. And accordingly the noise margins are calculated by the standard formula, and for another important parameter is the speed, that is the propagation delay for output going from high to low or low to high, which you can see is relatively higher compared to TTL, okay. And of course, if the supply voltage increases, the speed becomes faster, okay. So, that is another important point that we take note of. Fan out is not limited by the current it can deliver, which we saw in case of TTL, but amount of propagation delay it can handle. Static power consumption is very low. This is another important characteristics, and dynamic power consumption is one important consideration here, which is one path is there that half CV square, right, in during charging, and discharging the similar power consumption is there, okay, the same half CV square. So, together it is CV square that you can see, and as many times it is getting charged and discharged in one cycle given by the frequency of operation, right. So, together you get the dynamic power consumption because of the output capacitor getting charged or discharged, and the power that is getting consumed during the transition period, that brief time that you have seen when both of them are active, that being very abrupt, and so we can neglect that. So, roughly it is guided by this power that you see over here, and with high frequency it comes in the range of milliwatt and becomes comparable to TTL, okay. That is we take note of here. Fine. So, we go to this is one beautiful thing about these MOS based gates. Okay. So, when we look at development of NAND gate or NOR gate or combinatorial logic, we do not need resistive elements and other things that was there in BJT based circuit development. So, in NAND gate development CMOS, we need for every NMOS another corresponding PMOS, okay, to get the advantage of the CMOS circuitry. So, NAND gate development, we have two NMOS in series and the corresponding PMOSs are in parallel. Okay. So, any one of them is low, any one of them is low. What is happening? 0. Say VA is 0. So, this is in series. So, this path will not be there. This path is blocked. Say this is blocked by this one, right? When say this is 0, this is 0. Okay. But at that time, the corresponding VB, so this is 0 means this is now this PMOS is on, right. So, the output is getting the VSS over here through this. Okay. So, the output will be high. Is it clear? So, any one of them being 0. So, there is a parallel path here at the output providing the voltage and the current, the power supply, and in the series any one of them is blocking it, is blocking it. Okay. So, that is how what happens when it is both of them are 0, and when both of them are 1. So, this is 1 and this is 1 high. So, this is on, right, and this is off as well as this is off. That is how the PMOS will work. So, this is connected to the available to the ground is available over here. Okay. So, logic low voltage is available. Is it clear? So, that is how the NAND works. NOR is similar. So, these two will be now in parallel and the PMOS will be in series, right. And extending it further, we can develop many kind of combinatorial logic by different combination of this. So, this is also something by which people are which is drawing becomes a bit easier. So, this presence of bubble over here actually signifies PMOS. So, this is the symbol of a PMOS in that fashion, and this is the symbol of an NMOS, absence of this. Okay. So, these two are in parallel and corresponding these two are in series. This is in series with the other one. So, the whole of it, the what corresponds to B and C, what corresponds to B and C, okay, in PMOS, right. So, that will be in parallel with what is there as A over here. So, that is how the combinations are formed, and this particular combination, right. So, this is B plus C ANDed with A, right, and there is that inverter. So, that is how you get the logic, and many such combinatorial logic can be developed by simple interconnection of this, which is much easier compared to what you had seen in case of other logic family that we had discussed. Okay. Now, if we take this a bit further, so in the left hand side what you see is a circuit, right, where the NMOS and NMOS over here is in series with two PMOS that you see. They are not in parallel. If they are in parallel, then there would have been a NAND logic forming. The other thing that you see here, at this input between them there is an inverter present. Okay. So, what is it, what does it do actually? So, in the inverter this En is 1. Okay. So, this NMOS is on and this is inverted means this is low. Okay. If this is high, this is low. This low means this PMOS is also on at that time. Okay. So, the output will at that time will totally depend on whatever is the input. Okay. So, when En is equal to high, so this is on, this is also on, and output follows the input. There is the inverter logic, so it will be the inversion of it. But when input is low, what is happening? This is off, and this is also off, because it is at that time this is high for a PMOS makes it off, right. So, both of them are off. So, irrespective of the presence of A, the output is neither high nor low, neither it can drive, that is not, nor it can sink, that is also not possible. Okay. So, this is the condition we say is tri-stated, which is neither high nor low, and it offers high impedance, it is electrically offering very high impedance. So, similar thing can occur if we have a circuit like this. The previous stage is enabled bar plus A, that means enable complemented or A, and the NMOS is driven by enable ANDed with A. You will see when enable is 0, okay, then this is 0, right, and this is 1. So, the output will be, this will be high and this will be low, which will ensure that both of them are off. So, output is electrically isolated, offering high impedance, and only when enable is high, right. So, it is A which decides the output. A could be many other things in the previous cases. So, these are the tri-stated configuration using CMOS, okay. And this is open drain. So, open drain, how it works? Similar to open collector. So, only issue is that this PMOS now, when is replaced by the external resistance, the pull up resistance, there is a protective diode which is used in these particular cases. In CMOS circuits, these protective diodes are there in input stages as well to avoid surges, okay, because the static voltage is a very problematic thing in CMOS based circuit. And this one, another stage is over here, which is when it is connected, another such say wired, another such circuit which is connected over here, okay. So, then the logic together is providing wired and similar to open collector. So, this is what we take note of from this particular discussion. Finally, last part of our discussion, okay, CMOS circuits are there, TTL circuits are there. There could be cases when for less power consumption, more packing density, we are preferring say CMOS, right, and higher speed and associated benefits, we are thinking of using TTL, and then we want to connect these two parts for getting both the benefits. So, then we need CMOS and TTL interface, right, and to get CMOS and TTL interface, when both of them are being using say 5 volt supply, the corresponding parameters for input VIH, VIL, IOH and all. So, this is what I have taken from the transfer characteristics that we just discussed, right, and TTL I have taken from the earlier lecture we had. So, these are the two columns where the different parameters have been put forward. So, when TTL drives CMOS, so TTL drives CMOS, when you compare you will find that no issue with the current level, because CMOS requires very less current, okay, of the order of picoampere, and voltage levels are also fine, except only one case where the VOH TTL, right, VOH TTL, which is of the order of say 2.6 volt. In our earlier discussion we have seen from the transfer characteristics, with loading it can go up to say 2.4 volt or so. This is your VOH, that is the output high, okay, but the input voltage that is required by CMOS for the input to be considered high is 3.5 volt for 5 volt cases, right, and 10 volt cases we have seen about 7.5, 8 in that range, Okay. So, we are comparing because both need to be having same power supply 5 volt for the compatibility. So, 5 volt is what we are considering here. So, this is higher, right. So, that is what is only the problem, otherwise there is no issue in connecting CMOS load to TTL. And for that what people use, how it is overcome? It is overcome by having, this is the TTL stage, this is the output stage. Okay. So, having a separate pull up resistance, external pull up resistance that you see over here, right, which actually increases this voltage level more than what it was in this, what you can get in normal TTL cases. Okay. So, the voltage will be VCC minus whatever IR drop, voltage drop is occurring here, which will be more than the required 3.5 volt. Okay. And this voltage, the resistance, it has been saying to get voltage higher than this 3.5 volt in the order of 2 to this 2 to 6 kilo ohm, this kind of resistance would do. Okay. So, this is what is required, and when CMOS drives TTL, right. So, CMOS is this side, TTL is the load side. So, again if you compare the voltage levels and all, you will find that there is no issue with the voltage levels. Okay. So, the issue is there, the current it can sink. Okay. So, the current it can sink in the case IOL CMOS. So, this is the current, it can sink 0.4. Okay. So, it is sinking. So, sinking, so that is why it is told positive, and IIL when input is at logic low, right, the current it is coming out of the input transistor of the CMOS is of the this minus 1.6 milliampere. So, this is much more, right. So, if you just connect it, so this is going to give problem. Okay. So, to overcome that, what is used is a CMOS buffer only. After the CMOS gate, another CMOS gate will be put with appropriate dimension, larger area also, which will enable more current to get sunk. Okay. So, by which in some standard ICs made by manufacturers, say Texas Instruments and others, so it has been seen that the current that can be sunk is of the order of 4 milliampere, which can take say 2 standard TTL also. Okay. And if it is a low power TTL, more such gates can be connected. So, this is how the interface has to take place. Issues I have mentioned, and the issues are coming from comparing the transistor parameters for gate parameters for these two cases. Okay. So, references is mostly taken from the first one and some technical documents, and to conclude what we have seen that NMOS inverters can be used, but NMOS load resistance is preferred for less space, and CMOS inverter are useful in the sense that the charging and discharging are quicker, and also it takes the static power, there is no static power consumption. And if you look at the transfer characteristics, there are 5 zones depending on operating condition of the two transistors, whether they are in conducting or not conducting. If it is conducting, whether it is in linear region or saturation region. The fan out is not limited by amount of current, but the propagation delay, amount of propagation delay we can tolerate. Okay. And because more such thing connected, more such capacitances will come in parallel. Dynamic power dissipation is the important consideration, and it becomes a bit comparable at higher frequency, and it can have tri-state and open drain configuration, and TTL and CMOS gates are incompatible on few counts, not all the counts, and that can be appropriately taken care of when TTL and CMOS gates are to be interfaced with one another. So, with this we end the week 1, the first module. because of the time flag and other things, certain things we have touched in a manner for which greater discussion in the references can be referred to, or supplementary material can be also considered. Thank you.